start here. Thanks for joining us during this webinar today. So, my name is Velmer Fleischmann. I'm a mechanical engineer. I've been working more than 15 years with simulation with different softwares, as you can see here. And now, currently, I'm engineer and business manager at Virtual.PYXIS. So, Virtual.PYXIS, we have some offices. I'm here in Chicago, US, but also we are in Germany, in Hanover, and we have a partnership with a company called Virtual.CAE in Brazil. And also we are very close to ESSS, which is a company which represents ANSYS in South America, and ESSS is helping us to develop the ACT, the ANSYS Workbench integration inside this ANSYS workflow, as you can see here. So we are working together to have this integration. So what exactly topology optimization, the main topic today? Topology optimization is something that you can use for create a new design with minimal weight. So for example, here in this case, you have a called extended design with some loaded condition represented by a person, and a restriction, in this case, the contact with the ground. So topology optimization is the way that you get the best design. The software take away the excess of material, and finally you get a result like that. Of course, that you can control the manufacturing condition, but today you can see a lot of work about 3D printing, additive manufacturing. So topology optimization plays a nice role about this, because you can now print more parts without being very restrict about this process. So 3D printing helps the topology optimization condition to have a more specific and more robust design. So Virtual.PYXIS is a topology optimization software which transforms an extended design. So for example, starting with this condition of the gear and getting the minimal weight and maximum stiffness like that. So after the interactions of to get the equilibrium, you get this final design with minimal weight, and also applying some manufacturing conditions. And so by using this, the software delivers you some improvements, including, for example, less weight and greater efficiency, better performance, and also reducing your development costs, because you get the final result faster and with less material. And also we have been applying this methodology for different kinds of companies, for example, aerospace, automotive, biomechanics, electronics, machinery, medical equipment, oil and gas, everything which has engineering, design, we can apply topology optimization. So we also are a partner of ANSYS, so as an official partner. The main idea is because we have brought Virtual.PYXIS inside the ANSYS workflow. So the main idea today is to show you a nice integration process, starting for example with a concept using SpaceClaim. So you can try to design the maximal material condition, and after that the software you try to get away as much as possible mass from this component. So we use this as a real component, which is engine mount support. And after that, I will show how to apply the topology optimization, integrate to ANSYS, and you get a final result, something like that. After that, in this case, we used SpaceClaim to remodeling this new condition of, so from starting to get, after getting this STL file of the optimization, SpaceClaim is from the ANSYS group, is an ANSYS solution. You get a very fast condition to remodeling this new design. And also, I will show you how to integrate this to, for example, using the ANSYS DesignXplorer to get the best condition, for example, of minimization of stress of some part of this model. And finally, the static validation using, for example, MAGMA, and also again running with ANSYS. And here you show an ACT that we have created to import the MAGMA residual stress to ANSYS Workbench, and after that you analyze your model. So start with the topology optimization. For example, here I move to the ANSYS window. I will create a new Virtual.PYXIS environment. So just to show you what we have here. So this is a static nonlinear analysis condition of a real engine mounting support. So for example, here you see all the components. So starting with, for example, you have 4 screws representing or giving, which you will use it to give the bolt loads, giving a press fit between these 2 parts, the support and the engine block. You have the support itself, and also, as I told you, the engine block. So here, for example, I also can show you some contacts. We are using the nonlinear contact in between the support and the engine block. So here you see the regions of this situation using a frictional coefficient of 0.15. And bounded contact represented the both thread and the support, and bounded contact here connecting the screws into the engine block. And also the material property of this support, I didn't mention you, but this is a casting. So in this case, are you considering the material as a cast condition? So the mesh of my model here, I use 10 millimeters body size control for the support. Sorry, 5 millimeters, which is from for a topology optimization is good, because in this case you try to get an uniform element size for this situation, for this component, which also give you the possibility to get a better topology optimization result. If you have a small element and a big element in the same condition, sometimes you don't get a nice topology optimization result. So fixed support to complete the static analysis. Here the blue region, you're fixing the engine block, and also we apply force condition using this hole, and this force you are we are using 3 load conditions in 3 directions, and the maximal load here in Y acting at time 2. So time 2, time 4, and time 6, you can see the loads, the highest loads. And also both pretension, considering 36,000 newtons for the first load and lock, for others situations. So after that, you get the result of I'm here just show the last one, and also you see some influence of for example, the stress and also the energy, strain energy around the bolts region, and also you can see for every for example, for every time. But in this case, I go to prepare the topology optimization. So the first condition here, for example, I want to control my minimal element sizing to be, for example, 10 millimeters. In this case, I'm using 2 times the element sizing as I showed you before, 5 millimeters for the support. So here 10 2 times. Which is this minimal radius value. If you, for example, imagine a circular beam cross section, this is, for example, this is the radius of this circular beam section. So my beam would have, for example, 20 millimeters as a diameter, which is more or less the minimal situation for not having very small parts to your model. So this is the minimum radius to prevent small parts of your model. So design entities, in this case, you consider the support for something that the software you change. Of course, that here you can consider more than one component, no problem about this. And going back, I forgot to mention that you can use ANSYS parallel processing to speed up your solution. For example, here I can use 4 processors because most of the time during the interactions is from, in this case, from the solver, in this case ANSYS. So using more processors, you can speed up your ANSYS solution. Here is not 4 times faster. It's like not like linear, but for sure that you have a shorter time. Next step, also I can create some constraint of volume here. For example, I can change the name, but as a volume constraint. In this case, I use as a condition 35% of my volume to be as a constraint of my optimization. So next step, I can create, or in this case it's pretty much recommended to create a load case combination, because I have 3 forces acting on this hole, and these forces, when you are validating this model, the forces are acting different times. If they were acting the same time, so there was no need to create this load case combination. But as you have separate load cases, you have to give the software the opportunity to maximize the stiffness considering these 3 situations. So the software try to get the best design from these 3 situations. So here I call the 3 steps, as I showed you before, 2, 4, and 6. I not consider the time step 1, which is the screw pretension, because the energy of the screw pretension will be present when you consider each of these steps. Okay, so in this case, also I have to say Virtual.PYXIS, which is my objective function. In this case, I want to minimize my compliance, which is the same as maximize the stiffness, because the compliance is related to the strain energy. So if I minimize the strain energy, in the same way I maximize the stiffness. Again, of sorry, in this case not the support, I'm not selecting it here, but the load case combination I have just created step before. Two more steps about the topology optimization. The first is, for example, I can create a new constraint and call it, for example, manufact. In this manufacturing condition, I can give the, for example, the possibility of the software create an automatic mid-plane of the demolding direction, considering this case the global coordinate system and the x direction. So if you see the x direction is this frontal direction of the support. And here I just confirm the support as this condition. One important situation, and we have run a lot of complicated models. You can have, for example, for the same design, for example, the support, you can apply different manufacturing conditions. For example, different demolding directions, X or Y, for example. And finally, I can create here a situation that I tell the software some regions of my model I don't want to change because, for example, I want to freeze these areas because they are in contact, for example, with the bolt thread. So I can use this function to prevent the software to change these areas. So here everything fine to run the optimization. So as I told you, you can start the analysis integrated to ANSYS. As I showed you that you use here the parallel processing. I will not, of course, that I will not wait for this because it takes some time. So I want to move to the final result of my model, and here you can see it in a faster way. So software interacts to the ANSYS interacts to Virtual.PYXIS about in 15 to 20 interactions, depending, of course, of each case, and if it's more situation that you have less interaction, the model is has no linearities or something like that. So here you have a nonlinearity, consider the contact with friction. So in this case, just to show you the final results. So I will show them the final model, and I use the threshold of 0.4. So this is nice because in this case you can see how the material is distributed to the support. So for example, you start with a very big extended design, and at the end the software try to place the material, for example, create these ribs here, in a better way, and most of the time much better than an expert designer or engineer can create. So and also you see here there was a situation of manufacturing next, so you can use this without any problem to manufacture your model. So what we have, for example, at the end, you go to the directory and you will see here that you I can show you here, for example, you can create an STL file of your model, for example, with the threshold 0.4, and here you can create this STL file. So after that, using the SpaceClaim, for example, you can bring this STL file here, and you can create this new model using this condition. So, for example, to have an idea to get this final model, we took 3 hours using SpaceClaim. So you can compare this if it's good or not for you. But I mean, for creating a model in 3 hours is quite good. And so what we have done after that, we can also use some parameters inside here SpaceClaim. In this case, you have a parameter for this extrusion of this face, and also the radius value of this situation here, because when you go to the analysis, and I'm talking about especially the time 2 of the analysis, going back here is the force in y direction, is the maximum force. You see a stress concentration on this radius. So here I consider, for example, what would happen if I change this radius, or I get a thicker situation for this wall, trying to change the radius, trying to change the stress condition of this maximal area region. So in this case, I want to get the best design to fit my condition. So moving back here to my presentation, as I told you, we designed this using SpaceClaim. So extend the design, export in STL format to generate from the optimization. After that, exporting to SpaceClaim, and working to generate a new model condition. So the next step is the parametric optimization, where I can complement, and it's not like a competitor of the topology, but as a complementary situation. In this case, using the design exploration, as we have here a lot of windows, you show just the slides. So here, for example, you have your standard model, the geometry, and when you create these parameters inside the design SpaceClaim, these parameters, they are shown here, that you have these parameters, and you can use them for parametric optimization. The design exploration there is a specific model inside a Workbench workflow, and there are some options. For example, direct optimization. In our case, we have 2 input parameters, the radius and extrude. If you use direct optimization, the software, you need hundreds points, design points, to get the best, which is the minimum weight and stress constraint. So this direct optimization takes a lot of time for this case. Parameters correlation, in this case, you get when you have, for example, 5 or 6 input parameters, you can compare these parameters in the way how they affect the output parameters. So you get the most important, and you, for example, you freeze some not so important input parameters. In our case, we use both the response surface and the response surface optimization. Response surface, we create here design of experiments. From these 2 input parameters, we generate 90 design points, And after that, the software creates a response surface trying to fit these 90 points in the space. And after that, after creating this surface, the software automatically optimize and try to get the best condition. So response surface and response surface optimization, you have to create it together. And finally, you have also the Six Sigma analysis. I'm pretty sure that everyone here knows about Six Sigma, and you can use it from this tool, the design exploration. So here, the two parameters that we are controlling, the radius and the extrude. Just to move it back for someone who doesn't know how to create a parameter inside the software. So what you have to do, for example, you just press the radius, for example, and here you have the round to control it. And when you try to pull these radius and you move it to groups and you create new group here, you see that now this radius works as a parameter. For example, if I use here 3, the software change it to 3 this radius. So this is the way inside SpaceClaim for the user, a SpaceClaim user, how do you create parameters. So use the pull, for example, also for the extrude or a radius. You move here struct to groups and you create a new group, and the parameter is done. You can use it for parametric condition. So here, and also I want to move back just to show you the equivalent stress, for example, of the radial. So just to have a filter of this. If I use it here, for example, 100, or it's time it 6, now I use time it 2 in this case. So you see that the radius is the most critical part from the extended design, but also from the optimizing model. So that's why I'm parameterizing also and try to see the best condition for these radius. So the radius is a parameter in the extrude also. Those are the input parameters. And a constraint, you control, for example, the maximum von Mises stress of this area of this radius, and the limit for this case is the material yield stress is around 300 megapascals. So you consider as a safety factor of 2, the maximum is 150 megapascals. So the objective function in this case, you want to get the minimum of the mass. So because I have to, the challenge here is how to combine the best radius and the best extrude to get the minimum mass and also to control as I want the stress. So the first condition, you go back to the parameter set, and as I showed you before, and from the parameter set here, and also in this first situation calling the first step of the parametric optimization, you create the maximum and minimum condition of these parameters. For example, an important thing, when you bring the parameters to Workbench, there is a specific first ladder for this parameters. For example, if sometimes you create it, you don't see. For example, you go to the geometry here, and from you have to enable the the properties to show this right window from view. After that, you press geometry, and here you see parameter key, ds. So every parameter from ANSYS, or in this case SpaceClaim, which starts with ds, like ds of radius, ds of extrude, ANSYS understand that it is a parameter. So if you don't use ds, the ANSYS will not recognize. Of course, that you can use ds on that window and use everything that you want to control this. So in this case, the parameters are the same as a maximum and minimum. For example, minimum and maximum are of 1 and 6 for the radius. And here you see the two situations. So my design support these two conditions, and also the extrude. So here 1 millimeter is almost the same level of this surface, and with 6 millimeters here is much higher, and let's see, we can see what happens. So inside ANSYS also you have the possibility to control stress, and here, for example, the maximum you can use P or maximum, in this case is maximum, as a parameter, and also here the block, the property, the support, the property, the mass, you can use it as a P, which means property. So this window I show you exactly like that. So the stress, and just remember this number 230 or almost 231 is the maximum from the starting design, which is just that one we got from the SpaceClaim redesign, and our limit, as I showed you before, is 150. So it's above our limit. And also we have P as a mass. So the starting point is 2.96 kilos of this support. So the design of experiments I created using the design exploration. If you see here, as I mentioned before, you have 90 points. And in the first condition, design exploration try to get the minimum and maximum of each input parameter, and try to solve using ANSYS in this case to get the output parameter of every condition. So this is a way to, if you imagine some points in the space, and this enables the software trying to create a surface to connect these points. And also after that, I can use the surface to get the minimum of my expectation. So after the design of experiments, I move to the response surface. And here some results of this response surface. So this is the processing after the design of experiment. And a nice situation, I will show you 3 or 4 results. The first one is the maximum and minimum of each output parameter. So here you have the minimum of the equivalent stress and the minimum of the solid mass, and the maximum of the equivalent stress and the maximum of the solid mass. So the answer of the question, which are the input parameters here, ds rate, ds extrude, to get this condition. For example, forgetting the minimal equivalent stress, you have to use 6 and 6 for both parameters. For mass, you have to use 1.5 and 1. In this case, for the maximum, is pretty much the opposite. You have to use 1 and 1. So in this case, minimal radius and minimal extrude. Of course, in this case, if you have minimal extrude and a small radius you have less, you are maximizing the stress. So these are the highest value, and the same as the solid mass. The second result here is talking about the sensibility. So, for example, talk about equivalent stress, the maximum equivalent stress of the area. We can clearly see that the radius here in red color has more influence comparing to the extrude. So if I would change if I have the chance to change the tool about stress, I will be more effective if I change the radius compared to the extrude. On the other side, if I talk now about solid mass, the radius has just a little influence, but the extrude has a big influence on the variation. So this is a nice situation, because here sometimes it's not very clear for you what you can use, what you can change to get your what you want to achieve. Another result of the response surface, just a comment. I forgot to say in the beginning, if you have any questions, so from now we have more or less 5 minutes. If you have any question, you can write on the chat, and you try to answer some questions. So here, for example, this graph, you can see both input parameters, in this case, for example, the extrusion and the radius, and you can compare these input parameters, what happened about the mass and the stress. So, for example, talk about stress. If you get the maximum of each parameter, for example, this point is the maximum of extrusion, which is 6, and also the maximum of the radius in this point, again, 6. So for these two combinations, have the minimal stress. For the mass, we see here that talk about radius, you can vary from the beginning of the range to the end without having much influence on mass. But for example, if you move to the extrusion to this part, you got higher mass. So this result is telling you that use as much as possible minimal values for the extrusion. And optimization, in this case, so the software, after that, you take this surface and you give the software, just moving back here, exactly this condition. So after the surface, you tell the software, I want to have lower than 150 for stress and a minimal mass. This is after this all this procedure, and giving the software that condition, it shows you the best candidates. For example, my situation, the software is showing 3. I will get the first one because here I'm below 150, and for these 3 candidates, I have the minimal weight. So this is 3 points here in tons. If you see here, so it's 3.1 kilos, 1.3, 3.16, 3.18. So this is the minimum of these 3, minimal mass, and also being below 150. And from this graph, the 3 candidates also can see here, for example, the stress. If go this, I'm going higher. If go is lower, so I get the minimum of the stress for these 3 very close. But here I can see the minimum of the mass, higher, lower, so get the minimum. This is the first candidate. But for example, this stress not the mass because it's a real number, but the stress is calculated using the surface. So what we do at the end, we take these two parameters. For example, the best, the radius is, for example, 5.95 here, and the extrusion 3.42, for example, here. And we use these two parameters to feed ANSYS back, and after that we get this as a ANSYS reanalysis. So instead of 148, we have 138, for example. So this is a real ANSYS result. This is a result from the surface. But again, you got less stress than 150. And here the 3.13 here kilos are the same. So this is the comparison of these two situations, just to show you. For example, here the S is the design exploration. So before and after, talk about math, and before and after, talk about stress. So the after design exploration situation showed, for example, 6% higher mass compared this to this, but a very important stress reduction of 40% from the beginning to the end. And also for this situation, the stress of our after design exploration situation, we get stress below the limit of 150 as we desired. So for this, after the X, we use these two parameters as we start. I forgot also to mention you that the starting point from this, our radius was around 3 millimeters, and the extrude was around 1 millimeter. So 3, the beginning, the best is almost 6. 1 from the beginning, the best is 3.42. So here at the end we have the static validation. So now we have, just to summarize, we have the topology optimization, distributing the best material for your part. Inside ANSYS also you can, using the same workflow, you can have a 3 hours work for this support to remodel it. And after that, you can use the parametric optimization to get some better stress distribution, and also keeping the minimal weight as possible. Of course, that you can use any parameter of SpaceClaim. And finally, to show you something new that we have just created, is brand new. It's an integration with the MAGMA Software. So, for example, this is a free ACT that you can ask us and you can share with you who is using, for example, MAGMA Software. So you just enable the ACT as the standard of your ANSYS ACT, and after that you see here the condition that you can import. You can use it from the ANSYS tree. And just to show you, for example, in this case, this is a kind of universal file that MAGMA can export from your model. So the procedure is we prepare the mesh using the ANSYS Workbench. We export the mesh, and MAGMA runs its own mesh, and at the end, MAGMA interpolate the MAGMA mesh result to the mesh that we exported using, for example, here this command of ANSYS, here solution write input files. So this is the way we send MAGMA people this mesh information of my model, for example, like this. So for example, just to show you here, this is one element, and here I have 4 integration points, and I have the stress 1, 2, 3, 4, 5, 6. So the 6 components of the stress tensor of each integration point. You can use the integration point, or you can use the 1 point element condition. So in this case, you would have just 1 line for every element, but integration point, you will get a better result. So, for example, after this procedure, you just say which path is this file I have just shown you, and after that, here you see the residual stress of the MAGMA condition. As is a cast component, you cannot forget to use this information, because for example, you can have a high stress around this critical radius. If you neglect this information, perhaps you have a wrong result. From this step, you have the version 1 of our ACT. We are importing just for a while residual stress, but very soon, in between 1 to 2 months, we will implement also to import variation of young models. MAGMA export this information, and also variation of yield stress and tensile strength. So you can use this information very soon. And also the young models, sometimes it varies from part to part of your model, and the yield stress, I told you, can influence, for example, if you're using the plasticity analysis, you can use a new young models, a new young yield stress and tensile strength to prevent or to use the right plasticity information of your material. And just a final window to show you that after using this time 2, it's the maximum Y force, you have lower than 150. Here is 145. So also including the residual stress, in this situation we have it lower than 150. So please do not forget to use, and we have a custom model to see if the stress from the residual stress is important or not. So here just finalize my presentation, and I just want to see if there is some questions. No questions. I can wait some seconds or some minutes. If you want someone to have it, you have received this information of our webinar. So here you let this slide in here, so you can get my email. And if you want to send some questions also, or request something for us, you can use it. Also, you can visit our website, Virtual.PYXIS.com. So I think it's a nice workflow condition, because today you have to use as much as possible the software, trying to get the best design and also approve your model in a fast way. So in this case, I show you that you can integrate topology optimization and parametric optimization to get this information. So, gentlemen and ladies, if there is no question here, I thank you so much for joining us today. And we keep in contact. If you have any question, again, you can send me this information. So, bye-bye.